This video is about converting large cogeneration plants to gas generated from milled peat. Trying to replace gas, fuel oil, and coal in such 100-off megawatts plants will result in burning whatever is available. It is clear that wood chips were in short supply for many years before the current crisis. And the price of it will continue to rise, and everything will end with very strict state logging regulations. Today, it is already obligatory to mark small diameter trunks with holographic tags. It is almost impossible to supply a plant with firewood. There is not much choice left: straw, biosilt, peat, and the like. In Western countries, peat-fueled gasifiers, which I will talk about now, have been operating for decades. There are even cogeneration plants operating on milled peat with 500 megawatts per hour of output power. We, as usual, have never heard about them. Let's fill this gap. In this video, I will tell you about similar gasifiers that operated in the USSR. I will also show that it is not so difficult to make them today. Why are fluidized bed gasifiers suitable for large cogeneration plants? Because layered gasifiers are limited by their capacity. They can give several megawatts of power, being a few meters in diameter. It is not possible to indefinitely increase the shaft diameter. Coal-fired gasifiers have reached their technological limit, i.e. the maximum shaft diameter of 3.5 meters. Wood-fired gasifiers also have their own limit. Several megawatts of wood-fired gasifiers are suitable where there is no need for much gas power, in grain dryers or small boiler stations. It is possible to get away and build one wood-fired gasifier for 10 megawatts. I know how to do this practically. But what to do when you need 50 or 100 megawatts in case of a small cogeneration plant? Building 15 columns of downdraft gasifiers? That's not convenient. Meanwhile, one fluidized bed gasifier can give 50, 300, and even 500 megawatts of energy, consuming trashy small-size fuel worthless for either downdraft or updraft gasifiers. It is more convenient to build one rather than a couple of dozens of small gasifiers with the same total diameter as that of a large one. A fluidized bed gasifier is 10 to 12 times more productive than conventional layered gasifiers. For example, a fluidized bed gasifier 3 meters in diameter produces 45,000 cubic meters of gas in a steam air blast. This is as many as 10 semi-mechanized coke-fired layered gasifiers of the same 3-meter diameter. No need to briquette fuel is another advantage of fluidized bed gasifiers. A downdraft gasifier will work on peat only if the latter is briquette. In a fluidized bed device, the fuel must be crushed to pieces smaller than 10 millimeters. Briquetting increases the final fuel cost sometimes twice its market value. It should also be mentioned that the efficiency of gasifiers will always be higher than conventional direct combustion boilers. Compared to conventional boilers, up to 30% of fuel can be saved. Today, with the soaring energy crisis, people rush to buy new boilers to rebuild boiler stations. Why do this when you can just change the burners on old boilers? Just the other day, I had a conversation with a man who told me that it cost him $10 million to replace the boilers in an industrial boiler station. I would rebuild the facility 10 times cheaper and 10 times faster. People often ask me why there are no such gasifiers anywhere else. But they are in operation, and a lot of them, but not in our country. In our country, this technology was lost in the 1960s due to the craze for cheap gas and oil. To make this technology work for us again as before, you have to pay. Most people don't want to pay, they just want to watch. Those who don't want to pay today will chop down furniture and burn the stoves in their apartments tomorrow, and charge their phones on a bicycle with a dynamo. Even the British and German industries cannot afford today's market price for gas. I've been working on this topic for 10 years, and I don't know how else to get the word out. Probably a total blackout and freezing out is necessary for people to start doing at least something in this respect. In this video, I will focus on peat and talk a little bit about lignite gasification. Fluidized bed gasifiers were created specifically to gasify these kinds of fuels. By the way, these gasifiers also work on grass, chicken manure, biosilt, and other rubbish. For example, on household waste, watch my video on waste gasification around the world. The link is in the description under the video. These devices are generally omnivorous. The first classic gasifier known to us from history was peat-fired, and not by choice but due to the necessity to save money. Engineer Bischoff made it in Germany in Lochhammer in 1839. He wanted to save on coke and coal for metallurgical processes. As we can see, the first gasifier was a peat-fired one. The first fluidized bed gasifier was also made in Germany, but 82 years later, in 1921. Germany historically has a lot of lignite, and, ironically, it is the worst for gasification. But not all evil is evil, and thanks to such terrible fuel, engineer Winkler came up with a fluidized bed gasifier. It ran on lignite crushed to 2 to 10 millimeters. It could run on air or steam air mixture. This first device was 13 meters high and 12 square meters in cross-section. It began its successful operation in 1926. These devices mostly worked in Germany and Japan. These countries needed gas for synthesis at that time. If I'm not mistaken, it was these gasifiers that Hitler used to make Fischer-Tropsch gasoline for his Tiger tanks and other vehicles. The first gasifier worked for BASF to produce gas for methanol synthesis. The discovery of this gasification method allowed the production of gas for synthesis on an industrial scale. Generator gas suitable for hydrocarbon production must contain more hydrogen. This is achieved by blowing steam with air or, even better, oxygen with steam. The amount of nitrogen decreases in the gas, and the process yields more commercial products. This gasifier produces gas as follows. Quartz, silica sand, or other filler is placed on a grate in a high tube. Air is fed from below the grate. The air blowers give high pressure, about 2 meters of water column. This air speed makes the sand move and mix with the fuel into a mixture. It looks like boiling water. Fuel is fed into this sand mixture where it mixes evenly with the sand. All this moving mass behaves like a liquid in which everything is mixed. Therefore, the fuel gasifies uniformly throughout the entire layer without gaps, voids, or sintering. This method of gasification failed to burn 20 to 30% of the carbon. Standard Winkler gasifiers were 23 meters high and 5.5 meters in diameter. 2,700 kilograms of fuel gasifies on 1 square meter of the grate per hour. The sand layer is 1.4 meters high. Its height increases by about 1.3 times during operation. Winkler gasifiers could operate as an air blast, a steam blast, and an oxygen and steam blast. The latter two methods reduced the amount of ballast nitrogen and made the gas suitable for the synthesis of ammonia and methanol. That's what this type of gasifier was built for. In the USSR, the first fluidized bed gasifier was built in 1939. It was a pilot device to test the process. The working prototype was built after World War II at the Institute of Nitrogen Industry in January 1950. It was designed to produce gas from low-grade lignite for synthesis. Its principle was similar to the Winkler gasifier, but some parts were made differently. Such gasifiers worked on 0 to 10 mm fuel pieces. Peat milled after extraction is 20 to 0.5 mm or less in size. 85% of the pieces are smaller than 10 mm. Table 76 shows that milled peat after extraction is very heterogeneous in size. Fine peat fuel was gasified in a layer of boiling sand usually 1 to 2 meters high. Particles unburned in the sand flew up. Air was supplied through tuyeres at the top to finish burning the particles off. Tests showed that the area of holes in the grate of such gasifiers should be from 2 to 5%. Powerful blowers blew air under the grate. Grate slot's width was designed so that the sand would boil. The airflow velocity was calculated from 1 to 2 meters per second. The process took place at 900 to 950 degrees. When the layer heated, the air velocity in the grate holes increased to 5 meters per second, but it decreased again to 2 to 3 meters per second after coming out of the sand. The shaft expanded above the sand layer, thereby reducing the flow velocity. The sand layer usually equaled 0.5 to 0.8 gasifier grate diameter, usually from 1 to 2 meters. The sand layer swells to a 1.2 to 1.3 normal height during boiling. Such gasifiers were mainly designed to gasify peat and lignite because of their junk nature and extremely high reactivity. The highest reactivity is in lignite, a bit lower in peat, then comes wood and hard coal. Due to its properties, lignite produced 3,000 cubic meters of gas from 1 square meter of the grate in such a gasifier. Other fluidized bed gasifiers could gasify 4,000 kilograms of lignite per hour per 1 square meter of the grate. The fuel had to be dried to a moisture content of 10 to 15% first so that it would pass through the augers normally and would not stick, as well as for the normal gasification process. There had to be no pieces larger than 10 millimeters in size. Therefore, the fuel was first crushed and then sieved. 10% of carbon was lost in the bottom and fly ash, in the Winkler gasifier a little more. The gas from the gasifier at the Institute of Nitrogen Industry came out hot, about 850 degrees. It was necessary to take out its heat to heat the steam to 100 to 200 degrees to be blown into the gasifier. This increased the caloric value of gas by 100 to 200 kilocalories. The heat exchanger, which took heat out from the gas, was very much abraded by flying ash particles. As you see, the air had to be supplied in strictly determined amounts, otherwise, the sand would not boil. For this reason, these gasifiers are not flexible in operation. You can't reduce their power like in a downdraft Embert gasifier to 10% and then ramp it up to 100%. Here, the gasifier only operated at the designated power. Here is another example of what a fluidized bed gasifier looks like. Let's look at the picture. It is a high cylindrical shaft, lined with refractory brick on the inside. The shaft was usually covered with 12 to 15 mm thick metal. There is a horizontal flat grate with holes in the lower part of the gasifier. The holes comprised 1 to 2% of the entire grate area. As we can see, the grate is 2.6 meters in diameter. So, the area of all holes should be from 0.053 square meters to 0.106 square meters. This gasifier was supplied with pressurized air by gas blowers supplying 1800 to 2400 cubic meters per hour in such quantity that allows air speed in the holes to reach 2 to 3 meters per second and recalculation on 0 degrees and 760 millimeters of mercury column. A cooled bar rotated over the grate surface with a speed of 1 turn in 2 minutes to rake the ash from it. To prevent gases from entering the fuel hopper, carbon dioxide with a pressure greater than in the gasifier by 200 to 500 millimeters of water column is fed into it. The sand layer in this gasifier is 0.5 meters thick. When the device starts to work, the sand layer increases to 1.5 meters in height. The layer density decreases 3 times during operation. So small particles of carbon fly up 5.3 meters height without turning into gas. Air is fed above the grate at a low speed. Its volume comprises 15 to 25% of the volume of the air fed under the grates. It burned the fuel, turning it into gas. The temperature was already 900 degrees and the pressure was 800 to 900 millimeters of the water column under the gasifier dome. In Table 41 you can see what caloric value gas from lignite on steam air or steam oxygen blast achieved. This gasifier could turn into gas 21 tons of lignite per hour. Experiments by Soviet scientists have shown the following dependencies, in which the fluidized bed gasifier would work properly. The ratio of sand layer height to the grid diameter should be within 0.5 to 0.6. The ratio of the boiling layer to the calm sand layer should be 1.5 to 2, i.e. boiling sand layer should not be more than 1.5 to 2 times higher. The sand particles must be equal in size. It is almost impossible to achieve this as smaller particles will still pass through a sieve. So, the ratio of coarse to fine sand particles must be no more than 5 to 6. Let me show one more interesting gasifier prototype operating in the USSR on milled peat of natural moisture. Since peat for fluidized bed gasifiers had to be dried to 10 to 15% moisture content, Soviet scientists invented a way to dry it already in the gasifier. They invented a new gasifier without the need for a sand layer. The fuel particles comprise this layer themselves. This new gasifier was loaded with extracted milled peat of natural moisture. Normally, peat in the ground has a moisture content of 90%. Extracted in summer and stored, the peat loses its humidity below 40%. Scientists conducted tests on an industrial gasifier at humidity from 35 to 46%. Humidity not exceeding 35 to 40% turned out to be optimal. The gasifier efficiency was 65 to 70%. In this way they killed 2 birds with 1 stone. They dried milled peat with exhaust gases by feeding it from the top of the gasifier shaft where the temperature reached 900 degrees. The milled peat with a moisture content of up to 35 to 40% fell on plates in which holes were made to let hot gas pass from bottom to top. Above the plates, agitators rotated on a shaft discharging the peat down through the holes. The outgoing gas became 3 times colder and the heat exchanger was not needed anymore. The lowest fuel drying platform was made of fireclay bricks, those above of heat-resistant stainless steel. These plates were placed on water-cooled pipes. The lower platform was heated to a temperature of 900 degrees by the exhaust gases. As the peat particles fell down from the top, they dried, emitted gas, and, having fallen down, burned down, leaving ash. 1,300 kilograms of peat on 1 square meter of the grate per hour were gasified by air blowing. The air could be both normal temperature and heated up to 200 degrees. By the way, this type of gasifier produced almost tar-free gas. Comparing this gasifier in terms of capacity with similar diameter layered gasifiers, we can see that it developed 3 times more power having the same column diameter. Air was supplied from the bottom under the fuel, and it seemed to hover. This gasification method was called suspended bed. The sand was not used in it as a filler. When the ash adhered to the walls, it was broken up by a rotating crowbar moved both in a circle and up and down. The first small industrial prototype was 8.5 meters high. It was made of fireclay bricks and covered with metal sheets from the outside. The outer diameter was 2.3 meters, and the inner diameter was 1.1 meters. The thickness of the brickwork wall was 600 millimeters, taking into account the external insulation. Other reactors had a 370 mm thick fireclay layer. The reactor had a cylindrical shape from the inside tapering to a cone only at the bottom. The cylindrical part height should give fine fuel enough time to semi-coke, not depending on the performance of the device. The tapering cone was 2 meters in height. The narrowest crosscut at the bottom was 245 millimeters in diameter. The cone angle was from 18 to 40 degrees. It aimed not to allow particles larger than 0.25 millimeters to be blown out of the reactor. This particular model used peat from 0 to 6 millimeters in size. Increasing the blowing temperature by 200 degrees increased the gas caloric value by 200 kilocalories. The gas in this case reached 1,275 kilocalories. At first, the researchers assembled a small prototype, which dimensions I just mentioned, and then made even a larger one. This can be seen in the picture. The second gasifier was already twice as big in diameter. The inner shaft was not 1.1 meters but 2.3 meters. I think it gasified about 2,600 kilograms of peat per hour. The first device used peat 0 to 6 millimeters in size, and the larger one from 0 to 10 millimeters. The particles stratified in the stream. The bigger ones fell and the smaller ones went up. This stratification of different fuel pieces was facilitated by the cone expansion. The wider the diameter, the less the air pressure. This allowed lighter particles to reach upper layers. There was a large percentage of unreacted fuel carried away, which the cyclone returned to the lower part of the reactor. This fuel was no longer retained but flew up, burning along the way. There was a grate at the bottom with holes making 20% of its area. While fluidized bed gasifiers produced about 900 degrees hot gas, suspended bed gasifiers produced 380 degrees hot gas. The heat was taken away by the fuel falling from the top. It was semi-coking, while falling and semi-coking products were introduced into the gas, enriching the air gasified poor gas. Such a temperature greatly simplifies supplying gas to burners. The second type of suspended bed gasifier, similar to the one I described, was designed but never built. According to the author's idea, the second type of suspended bed gasifier was to retain up to 1 meter of fuel on its stairs with a large amount of combustible gases passing through. But it would not happen evenly. As you can see, there were fixed grates at the top. According to the idea, the gas was supposed to rise evenly up through them. No scraper was available in the lower part of the reactor to scrape the sticking ash from the walls. This 4.5 meter diameter device was designed for 5,000 kilograms of peat per hour. You can see similarities with the previous device, whose shaft was 1.1 meters in diameter to gasify 1,300 kilograms of peat per hour per 1 square meter grid, 1,430 kilograms per hour on the area of 1.1 meters. The larger model of 4.5 meters in diameter was designed to gasify 5,000 kilograms of peat per hour. As we see, such a device will gasify 1,430 kilograms more peat for every increase in diameter by 1.1 meters. This gasifier was never built on an industrial scale, but the first prototype, which I described earlier, was constructed, replicated for industrial use, and operated successfully. It can be taken as a basic prototype for construction. Or a fluidized bed gasifier, which will be 3 to 4 times more productive than a suspended bed gasifier with the same column diameter. If we compare fluidized bed and suspended bed gasifiers, we can say that both can run on air, steam, and steam-oxygen blast. The temperature is the same inside both types of gasifiers but differs at the output. A fluidized bed gasifier is 10 to 12 times more productive than a same diameter layered gasifier, while a suspended bed gasifier is only 3 times more productive. In a fluidized bed gasifier, the fuel must be dried to 10 to 15% humidity, and the fuel pieces should not exceed 10 millimeters in size. A suspended bed gasifier does not need dried fuel. The fuel dries out already inside the device. After milled peat is collected from the fields in summer and stored, its moisture content is about 40%. A suspended bed gasifier can operate at this but not higher moisture content. There are other ways to gasify milled peat. One of them was developed at the Peat Institute. It was technically easier to perform than the ones I described above, but required grinding pieces of fuel to 1 millimeter, i.e. to the dust. This raises the cost of fuel. But peat is great just because of its cheapness. If it costs as much as wood chips, then all the complications lose sense. Peat can also be gasified on a cyclone gasifier, where the size of the fuel and humidity are also critical. If someone needs to design such gasifiers, my WhatsApp is below the video. See you soon.